Hello from the new, old new studio. Not quite fully set up in here yet, but it's usable. And today we'll be talking about these. I don't think I need to explain what this is. If you're watching this video and you've got a 3D printer, you will most likely have already printed a 3DBenchy at some point. And I think that's great. I'm going to argue that this is pretty much the ultimate calibration or benchmark print. I have never printed a calibration cube, well, maybe once, but that was pretty much to show how much of a waste of material that calibration cube was. The Benchy does so much with so little material, and I kind of want to show you how to use them. There are a lot of hidden features and implications on the Benchy that really make it a model that is so far ahead of other single-purpose setup prints. And all of that after a message from today's sponsor. Microswiss make high-quality extruders, hot ends, nozzles and heat breaks for your 3D printer's toolhead. Their new NG extruder has an ultra-short distance from the dual drive gears to the hot end at just 41mm long, making for a compact and highly precise setup. Microswiss's nozzles and heat breaks fit many existing setups, and they all come with a low-friction, wear-resistant coating that reduces printing issues and enables you to use aggressive reinforced filaments. All of the products are manufactured in-house in the US, and you can find them at the link below. So I want to get one thing out of the way first, because it's a super common complaint when you start printing little plastic boats. I don't think printing these is wasteful, bad for the environment, or anything like that. First of all, we're talking about really tiny amounts of waste that we're producing here. The Benchy weighs about 13.5 grams, and when printed with PLA, which is derived from corn, causes about 60 grams of CO2 to be released in total, for the production of the PLA and for the electricity used to run the printer, which actually is the much larger part of that. For comparison, if you do a single 0 to 60 run in a traditional gas-powered car, this is about the amount of gasoline you're about to burn. It's about 80 milliliters from fossil sources, which is going to cause about 250 grams of CO2 emissions. So basically, for every 1 or 2 seconds of stepping on the gas, you're roughly doing the same amount of environmental harm when it comes to CO2 as printing a single 3D Benchy. That kind of puts a perspective on things. By the way, this is tea, quite delicious actually. And printing a 3D Benchy overall actually saves waste on your printer in the long run. It is much better to do a single small test print and then use that to tweak your printer than having to eventually throw away a much larger print because it had a flaw that you weren't anticipating. Plus, these are decorative, if you will. What makes a 3D Benchy such a great testing model is quite a few things actually. What I find most important is that it doesn't just cover a single tuning parameter. When you're making changes to your printer's setup, it is super easy to over-optimize for one single thing, because most settings you have access to affect a multitude of aspects on your prints. Some aspects you're going to improve, and others you're often going to make worse. For example, as you increase temperature, within reason, you're going to get stronger parts, but your bridges are also going to be droopier, you are going to get more stringing, and you're going to get worse top surfaces. As you increase jerk and acceleration, I think that was this one maybe, you're going to get rid of ridges on round edges, but you're also introducing ringing and extruder control issues to your prints. Because the 3D Benchy has such a wide range of feature sizes, geometries and details, you're always inadvertently also checking for all those areas where you might have made something worse. But the 3D Benchy isn't a benchmark just for benchmarking's sake. I've made some test parts in the past that really hone in on some specific details, but what the Benchy does is try to be realistic. There are no crazy long bridges, there are no details that are smaller than your nozzle, there are no crazy overhangs, and that is sort of what your typical 3D print is going to look like too. Very rarely are you going to work with parts that are not in some way optimized for 3D printing. But this has also become a bit of an issue for the Benchy as a torture test. When the Benchy first came out, it was an actual benchmark test. You could clearly see the differences between printers. But nowadays, what you can expect from 3D printers is a lot better than what you could then. And honestly, if an off-the-shelf machine can't print a near flawless 3DBenchy straight out of the box, I'm gonna have to assume that, the manufacturer is either lazy or incompetent or both, or the machine that I got is broken. Before we go over all the things to look for in a Benchy, let's briefly touch on how to print one. First of all, I think this should be obvious. Don't use any special profiles or settings for it. Print it the exact same way you would print any other part as well. If a profile has issues as is with printing a 3DBenchy, those issues are going to show up in some other print at some point too. And secondly, also print the Benchy as is. Don't change its geometry, and especially don't scale it up or down. A big Benchy like this with thick, smooth layers, a matte finish, that just looks great. This is a Filament Gentleman's Grey PLA, link in the description. It is a pleasure to look at, right? Except for that layer skip up here, my bad. But as far as benchmarks go, this isn't representative of anything really, and it completely erases the ability to compare the Benchy of one printer to Benchy printed on a completely different machine. All of the features are much larger, obviously, but that makes some of them easier to print and some of them harder to print. So you can't really make any deductions with a print like this that isn't done at 100% scale. The Benchy, at its intended size, is small enough that it will fit on virtually any printer, and I think that was a great part of the design goal too. Let me give you an overview of the things I tend to look for in a 3DBenchy and how they relate to your printing, aka your slicer settings. Starting with some of the more obvious ones. If there are issues with excessive warping, stringing, holes in the hulls of the Benchy, layer skips, fix those first. To even judge some of the more differentiated benchmarks built into the Benchy, it needs to be a fairly solid print and at least resemble the part you're trying to print. So with holes in the perimeters, check your extruded and hotted. If it's warping or detaching from the bed, make sure your nozzle distance is correct and the bed surface is suitable and clean enough for the filament you're printing. If it's covered in strings, like this one, dry your filament and make sure you're not printing too hot. Once you've got those settings out of the way, we can start looking at not just fixing the print profiles, but tweaking and improving them. The 4 bits that I look for first are the ones that you don't need any measuring for, though there are certainly enough opportunities on a 3DBenchy to use it as a full calibration cube replacement, and we'll get to those in a bit. First is the bow down here. Actually, let me show you on this one. This is a 40-degree overhang from horizontal, so somewhat challenging, and in a good Benchy, it should be smooth and even. However, if it has a little kick in on the bottom section right here, chances are your bed temperature is too high to allow the material in those bottom layers to fully solidify and resist the pulling forces from the layers above it. If there's more extreme issues like this crimping further up on the bow, you're most likely printing too hot, or you have insufficient or uneven cooling from the part cooling fan. Another good indicator that temperatures are a bit too hot, or you have too little part cooling, in this case specifically the minimum layer time that is too brief, is the chimney not printing crisp and sharp, but as a somewhat melty blob instead. So those are some of the temperature indicators. This one was printed with ABS settings and PLA loaded in the machine. Second, the quality of the top surfaces in the deck area back here. If you can see the infill poking through that top layer, either you have too few solid layers for the infill percentage you're using, which is what I did on this one. Less infill will require more layers on top to cleanly span over the infill structure. Or you're, again, printing too hot. This one has gaps as well. In this case, a top surface really is just printing many short bridges over the infill. And if the nozzle temperature is too high, that filament will continue to droop into those gaps as it gets printed. Now, if the deck area is flat, so it's bridged well but not filled in all the way, and still has gaps between the individual fill lines, that can be two things in addition to what I just talked about. The first, and maybe the obvious one, is under extrusion, which, this one was printed at 80% as well. But the second one takes us to the third area I'd be looking for, and that is backlash. If you have gaps in the top solid infill. That is one indicator that you might be dealing with backlash. The other indicators are, to a degree, gaps between infill and the perimeters, which is, somewhat hard to notice often. But most strikingly, the chimney up top. This is supposed to be perfectly round, as you can see in this guy. But if you've got backlash on one of the axes of your machine, it will start to deform towards looking like a coffee bean. The nominal diameter of the chimney's top piece is 7 millimeters. If one direction is significantly shorter than the other, that axis most likely has some backlash. All these print issues so far I've reproduced on a simple Prusa Mini by slicing the parts wrong. This one though, I've had to go in and loosen the Y-axis belt until the bed had noticeable slop. The fourth and last visual area is ringing at corners and at the opposite extreme, a loss of detail in those corners. Ringing is super obvious at the bow around these parts, because the printer has to do fast, short moves up here at the ridge, which has a really good chance of exciting any resonances in the motion system, and then it has to print the bow, which is a relatively large and perfectly smooth surface. What you're seeing now is archive footage from other printers because the Mini has quite reasonable firmware limits when it comes to how high I can push acceleration and jerk settings, so I couldn't get it to ring much. Ringing really is a function of how fast and how jerky the printer accelerates, how springy the motion system is, and how much dampening there is. A printer with long, cheap rubbery belts will most likely show more ringing than one with shorter belt loops and Gates belts. However, go too soft and dampened on a motion system, and you will start rounding out corners, sort of like the backlash example here. But this is usually much less of an obvious issue and perhaps not even relevant to how most of your prints will come out. Then again, unless it's at the very extreme end of how bad it can get, ringing itself is also mostly a visual issue. There are obviously also a bunch of other features on the Benchy that will inform you about performance. But this is actually one of the areas where I don't think it does a particularly good job, which is why the abomination of a test print that I designed a while ago actually uses most of its area for tests. Printers just have become really good with these features that, nowadays a Benchy isn't much of a challenge here anymore. So the other aspect to the Benchy is being able to check dimensions of the prints you create. Every single feature of the Benchy, be it its length, width, every single detail on here, they all have nice and round nominal dimensions. And they're all listed out on the 3DBenchy website, so I'm not going to go through all of them. But there is a key problem with trying to make sense of dimensions you're measuring off of any printed model. You're measuring two things at once. The first one being the one that is more intuitive, and that would be that when you tell your printer to move, say 70 millimeters, it actually moved, say, just 69 millimeters. This is the way a lot of guides talk about so-called calibration, that you would need to then go in and increase the amount the printer moves to make sure your part ends up at exactly 70 millimeters. The Benchy, by the way, is just 60 millimeters long, so yeah. But for the most part, that approach is wrong. While there are certainly deviations from the printer moving the wrong amount, when you measure comparatively small lengths, like a 10mm cube or any of the smaller features on a 3DBenchy, you're mostly measuring how much your part has sort of swollen up or shrunken down along the XY plane because of inherent inaccuracies of the filament printing process. And that is a fundamentally different calibration step than changing essentially the scaling of your parts. What you will find if you follow that approach is that while that exact 10mm dimension will now be absolutely accurate, as soon as you print smaller or especially larger parts, the overall scale of those will be wrong. So the approach to checking scaling and contour correction that I'd recommend would be to print the largest possible scale checker you can. I did a video using calibration sticks a while ago, and that is still valid. And once you have the overall steps per millimeter figured out, then go in and fine-tune the bloat of your parts with the XY offset option. But both of these tuning steps usually don't need much adjusting at all. If you find yourself making drastic changes here, I would first start looking for other mechanical issues on your machine and fix those. And you also kind of have to keep in mind that, filament printing isn't something that is 100% precise all the time. There are just some inherent inaccuracies from the machine, from the process. One more tip about taking dimensions. If you need to take scale measurements from a part like the 3DBenchy, always try to measure between two surfaces pointing in the same direction. That way, if there is an issue with bloat on your prints, it's the same amount and same direction on both surfaces. So effectively, it'll get cancelled out. So take a dimension like this. Okay, this doesn't work because this is too big. So take a dimension like this, where you're aiming for 32.5 millimeters between the top of the chimney and the top of the surface of the box. Or try to measure the 10 millimeters from the right side of the left box wall to the right side of the right box wall. If you just measure the overall 12 millimeters worth of width of the box, you are mostly measuring which amount of contour correction you'd need to apply to get back to zero. Again, there is a list of all the exact nominal dimensions on the 3DBenchy on their website, so if you want all the details, you can find them there. Now, to close this out, maybe some things that the Benchy doesn't do particularly well and that you will still need to check for with other tests if you want a full report on a printer's capabilities. I've just talked about it not being the greatest model for checking dimensional accuracy. It's certainly better than a calibration cube because it shows you how you might be messing up other dimensions when you just calibrate for one single 10mm length to be perfect. But to really hone in dimensional accuracy, you really need something larger than the Benchy. It's a similar story with its height. When a printer is not built particularly well, it can show wobble issues either at the halfway point of its z-axis travel or further up. And the 3DBenchy simply isn't tall enough to expose those problems. On the other hand, a 3DBenchy also doesn't have any particularly small features, like you would want to test resin printers. Or, even in the size range where you would see a difference between a 0.4 and a 0.6 nozzle, or between the old slick 3R slicing and the Ultimaker Arachne engine. The 0.1mm text on the back, which is a bit more visible in this one, is a nice try. But because it's just part of the perimeter and not a separate freestanding feature, it's not a particularly challenging area to print. But I think the biggest flaw of them all, it doesn't float. That is unacceptable. Thanks to my supporters on Patreon and YouTube memberships. I know it's been a rough couple of months, but we're getting back on track, slowly. If you think what I'm doing is worth supporting, consider joining too. In any case, thank you for watching, keep on making, and I will see you all in the next one.